Hi, so last lecture we ended by giving two constructions of fields. So the first construction we had was to take the quotient of some ring by a maximal ideal. And the second construction was to form the field of fractions of some integral domain. All right. Okay, so recall that for any positive integer n, we have defined n times 1, where 1 is some element of a field. So we've defined, in fact, for any ring, n times any element of the ring. So n times 1f, where f is a field. This was just defined to be n copies of 1 added together. And note that even though n is strictly greater than 0, it's still possible for n times 1f to be 0. So for instance, consider the field ZP defined to be the PID Z quotiented out by the maximal ideal generated by some prime P. And this is the field with P elements 1, 0, 1, up to P minus 1. We saw this last time. It's an example of the first construction applied to the maximal ideal P. Okay, so then for this field, P times 1 equals 0. Just because we're quotienting by the prime ideal P, so any element in that ideal has to have a representative, which is 0. So this here. So maybe I should say P times 1 equals P bar equals 0. Okay. Okay, so it's possible for a multiple of 1 to be 0 in a field. Definition. The characteristic of a field is the smallest positive integer such that P times 1 equals 0. So the characteristic of a field written CARF is the smallest positive integer P such that P times 1f equals 0, if such a P exists. and it's defined to be 0 otherwise. So for example, if we go back to the field with p elements for prime p, so this has characteristic p. And for an example of something of characteristic 0, you can take the rationals or the reals or the complex numbers. They all have characteristic 0 because it doesn't matter what integer you multiply 1 by, it's not going to be 0 in any of these fields. Okay, so a simple proposition. Suppose F is a field with non-zero characteristic then the characteristic is automatically prime. Proof? Well, this is essentially immediate from the fact that characteristic is defined to be the smallest integer p such that p times 1 equals 0. So suppose p equals ab for integers ab which are greater than 0. And let's assume, to try to get a contradiction, that a and b are not equal to 1. Okay, so if p was not prime, then I could factor it into integers which are greater than 1. So then we would have that since p is a characteristic, ab times 1 equals 0. But this is the same as a times 1 times b times 1 but since a field is an integral domain, then we must have a times 1 equals 0 or b times 1 equals 0, because fields are particular examples of integral domains. So we have that a times 1 equals 0 or b times 1 equals 0, but a and b are both less than p, since neither a nor b is 1, and since a times 1 equals 0 or b times 1 equals 0, if a times 1 equals 0, then a is less than p, violates the definition of the characteristic as being the least integer such that a times 1 equals 0, and likewise if b times 1 equals 0, since b would be is less than p, that would violate the fact that p is defined to be the least integer with p times 1 equals 0. So this violates the definition of characteristic as the least integer p with p times 1 equals 0. Okay. So the characteristic is always prime. Okay, here's a very simple lemma. Let F be a field of characteristic P then for any element in the field, p times that element is 0. And the proof of this is just very simple. So p times alpha for any alpha in F, well, that's the same as p times 1 times alpha, which is the same as p times 1 times alpha, but by definition of the characteristic, p times 1 equals 0. Okay. Okay, so let's now make a definition. For any field F, we define the prime subfield of the field to be the smallest subfield containing 1. So the prime subfield of a field F is the smallest subfield containing 1. So for example, the prime subfield of R is the rationals Q, because any subfield of the rationals containing 1 has to contain all of the rationals. For a different example, you could look at the field of rational functions with coefficients in Zp. So let's look at Zpx to find to be the field of fractions of polynomials with coefficients in Zp. Then the smallest subfield containing 1 is just Zp in this field. Okay. So let's give now maybe a more concrete description of the prime subfield. So we have a ring homomorphism phi from the ring of integers to the field F that's given by taking an integer n to n times 1. And by definition of the characteristic, we know that the kernel of phi is the ideal generated by the characteristic, because the characteristic is the least integer such that n times 1 equals 0. So then the first isomorphism theorem tells us that the image of phi is z modulo the kernel, which is the ideal generated by car of f. So we see if the characteristic is p for some prime p greater than 0, then image of phi is zp, which is contained in f, because the image of phi is always contained in f, of course. And then since any field containing 1 has to certainly contain all multiples of 1, because a subfield has to be closed under addition, we would see that if the characteristic is P, then we have the subfield ZP containing 1 and also being contained in F, which implies that ZP is the prime subfield of F in the case the characteristic of F is greater than 0. On the other hand, it's possible that the characteristic equals 0, think of the rationals, and then in this case the image of phi is the integers, and phi is just an isomorphism. So in that case, the image is only a ring and not a field. It's just the integers. And then in this case, well, the smallest field containing the integers, well, if it's a subfield and it contains the integers, it must also contain all fractions, because being a field, it needs to be closed under taking inverses. So in this case, the prime subfield is the field of fractions of Z, which is just the rationals. So if the characteristic is 0, then the prime subfield is the rationals. If the characteristic is P, then the prime subfield is ZP. Okay, and an obvious remark, since any field contains its prime subfield, then any field F is a field extension of its prime subfield. Okay, so let F in K be some field extension This just means to remind you that F is some subfield of a larger field K. So we often write a field extension as, so we often write this field extension of, so we say that K is a field extension of F, and we often write this as K over F. Okay, so suppose we have some field extension K over F. Note that we can multiply elements in K by elements of F. So we can certainly multiply any element in K by other elements of K. And in particular, we can multiply elements of K by elements in the subfield F. So in this way, we may consider the larger field K as an F module, just because we can multiply by elements of F. But F is a field. So this means we can consider K as a vector space over F, because F modules are the same thing as vector spaces, since F is a field. So we can consider the larger field K as a vector space over the smaller field F. And this gives us an important invariant. So we define the degree of the field extension K over F as the dimension of K when considered as a vector space over F. Note that this may be infinite. So, in terms of notation, the degree of K over F is written like this, square brackets K dot F, and to remind you, it's defined as the dimension of the vector space K over F. So some examples. Okay, for any field F, we can look at the field extension given by taking rational functions over coefficients in F. And then this will be a field extension of infinite degree. This is just because the vector space is infinite, since the set 1, x, x squared, and so on is linearly independent over F. For another example, we can look at the field extension C over the reals, complex numbers over the reals. This has degree 2, since 1i is a basis for the complex numbers as a vector space over the reals. Okay. Proposition. Okay, so let F be a homomorphism between two fields. Then F is either the zero homomorphism meaning that F takes every element to 0, or F is injective. Proof. Okay, so the kernel of any ring homomorphism is always an ideal. So kernel of F in F1 is an ideal, but F is a field, F1 is a field, and ideals in a field are either 0 or everything. And so F1 is a field, and the only ideals in a field are 0 and the entire field, simply because an ideal has to be closed under multiplication by arbitrary elements from the field, but if you have a non-zero element, then you can multiply by its inverse to get 1. And once you've got 1 in the ideal, you have everything. Okay, so we have two possibilities. Either the kernel of f is 0, in which case f is injective, or the kernel of f is everything, in which case f is a zero map. Okay, so let's end this lecture with one construction which will be very important. Take some polynomial in the ring of polynomials over some field f. And assume now that the polynomial is irreducible. Okay, so fx is a PID. And we know that in a PID, irreducible elements are prime. And further, we know that prime elements generate maximal ideals in a PID. So then we get that fx quotiented by px for p irreducible is a field. So this will be a very important construction of fields which will have lots of consequences. So let's see some examples. The first example would be Rx quotiented by x squared minus 1. It is, x squared plus 1. Okay, so x squared plus 1 has no solutions because the square of any real number has no solutions in the reals because the square of any number has to be positive. Okay. So observe that the element x bar in Rx quotiented by x squared plus 1 satisfies x squared plus 1 equals 0, or simply because this equation, so in the quotient we have x squared plus 1 equals 0, so x bar squared equals minus 1. Okay, that means now that we can consider x bar to be a number squaring to minus 1. So it's somehow linked to the complex numbers. So we define a homomorphism of fields Rx quotiented by x squared plus 1 to the complex numbers by taking a polynomial in x bar to the polynomial in I, and then you see that this is well defined because if I sub in I into x squared plus 1, I get 0. So I'll let you check this. Further, this map is non-zero. In fact, it's surjective. Just because I can take, for any real number, a plus bx, and then it gets mapped to a plus ib. And by what we've already proven, field homomorphisms which are non-zero are automatically injective. So it's non-zero because it's surjective, and then it's automatically injective. So it's injective and surjective, hence it's bijective. And in conclusion, we've just given an alternative construction of the complex numbers. So we've found an isomorphism from Rx quotiented by x squared plus 1 to the complex numbers. Okay. Okay, so let's just end with maybe a slightly different example. We could try to do the same thing, but instead of looking at polynomials with real coefficients, we can look at polynomials with rational coefficients. And then, once again, x squared plus 1 will be irreducible because it has no rational solutions. And then this is a field, and we can map it to the complex numbers in the same way. And it will be non-zero, evidently, because 1 goes to 1. So it's automatically injective. Okay, this is just a map p x bar, just as before, goes to pi, but now polynomials only have rational coefficients. So, so the image of let me call this inclusion of this field qx quotiented by x squared plus 1 into Cf, then the image of f is the subfield of C given by a plus bi, where a and b are rational. Okay, and now notice that this field is, so let's say MF, which is the field of complex numbers of the form a plus bi, where both a and b are rational. This contains the rationals. So the rationals are the elements of the form a plus 0i. And this is a field extension of the rationals of degree 2 with basis.